Okay, we're in this last chapter here, and we are talking about Le Chatelier's principle. And again, a reminder that Le Chatelier's principle is basically the idea, as we mentioned at the end last time, that we do have this system that's at equilibrium. So we got this reversible reaction, and basically it's reached equilibrium, which basically means that the rate of that forward direction equals the rate of the reverse direction. So as we talked about, what that will essentially do is lock everybody into place in terms of their concentrations or pressures, if you're dealing with pressures. And pretty much they will not change. So they'll just be able to maintain pretty much where they're at. Again, it doesn't mean that they're equal amounts on both sides, but they'll be able to maintain, pretty much where they're at. So what happens though is we could add a stress to this equilibrium. And when it does that, it's going to really kind of mess up the equilibrium. And it's going to make it not be at equilibrium at that point. But these type of reactions will always want to try to find their way back to that equilibrium sort of position. So it will try to get back to equilibrium. And as it tries to get back to equilibrium, it will basically do one of three things that we talked about. It will shift to the right, which means we'll make more products. That really means that the forward reaction will start to predominate. It could also shift to the left, which means we'll need to make more reactants to once again reach equilibrium. What that really means is you basically just kicked off the reverse reaction happening in this situation. And even though there sort of is something done to a system at equilibrium, there are a few instances where really you'll still see no change occur, even though you sort of did something to it. So those are sort of your three options. We sort of ran through at the end last time the different stresses that you could add. There's, again, concentration. There is pressure and volume if you're dealing with gases. There's also temperature, and there's a catalyst. So these are common stresses that you could add to the system. So what we're going to talk about today is going through each of these and talking about what happens to the equilibrium as we do that. So we're going to start with concentration first. And concentration is pretty much like what we saw in the experiment. So concentration, you pretty much could do two things. You could either add more or you can remove. And when we add more, it will always shift away from the side you added it to. So what that means is if you add more reactants, it should shift away from the reactant side and go to the product side and start making more products. If you add more products, it should shift away from the product side and head back to the reactant side in that particular case. When you remove something, it actually will go towards the side you removed. So again, if you remove reactants, it will go towards the reactant side. If you remove products, it will go towards the product side. Once again, you can almost think of it removing, if you want, like you create a hole on that side, and it just needs to kind of fill that hole. So that's a good way to remember it. And AA is a good way to remember add away for the first one. So again, I might drew this in the lab, but if you had, again, a system that is at equilibrium, and this guy was your reactant, this side was your products. Once again, if we basically throw somebody onto the product side here, we're going to get this situation to occur. And in this case, to fix it, we would need to put more people on the other side, so we'll shift away from the other side, and that will bring us back to an equilibrium state here. in that case. So when we add, it goes away from the side we added it to, again, really because it will kick off that reaction away from it. Again, if we had a situation where we were at equilibrium here starting out, our reactants, our products here, and this guy decides again to hop off, that's going to cause this thing to kind of come crashing down. Now to fix that, we kind of balance it back out by putting more people on the other side where we removed it from. And again, that's going to bring us back into sort of equilibrium at that point. So as we did in that lab, and as we talked about, if you want to add something to an equilibrium, you pretty much is simple. You could just go grab it off the shelf, and if you got some type of solution that contains, say, ions that are present in the reaction, all you have to do is add that, and that'll be a source, obviously, of ions in that particular case. If you want to remove something, again, that's a little bit more difficult, especially in sort of a solution situation, as you have ions basically just floating around in the solution. So typically, if we want to remove something, we could do one of two things. We could add something else, for example, we can add another ion, and when that ion comes in, say, reacts with the negative ion, maybe it makes a solid, and it starts to make a precipitate in this case. And that would be one way that you can essentially kind of go into a solution and remove something, is to add something that's not in the reaction but will react with something that's there, either to make a precipitate, which is very common. And another thing you can make actually is what's sometimes referred to as a complex ion. You could add something that will tie up an ion and not allow it to be free in the solution. And it may still be aqueous. It may not make a solid, but it may just be kind of floating around with it attached to it. And that, again, is a way to sort of remove something from a solution. Another very common way is kind of like one of the ones we had. If you had something like hydroxide, for example, in the solution, you could add something like an acid, which is H plus. That H plus and OH minus will make water, basically. And that would essentially be like removing hydroxide from the solution. Remember that both solids and liquids, like water, are not included in the equilibrium expression, and it doesn't have really an effect on the equilibrium. So those are two very common ways that you can kind of remove something. So when you're doing any of these type of situations and you're adding something, the first thing you want to check is whatever I'm adding a source of something in the equation? And if it's not, then you want to think about is whatever I'm adding something that will react with something that's there and perhaps make a solid or something of this nature. Any questions on that there? The next sort of relationship here we'll talk about is between, say, pressure and volume. And they oftentimes are tied together. And our friend Boyle, I think it was, right? P1 V1 equals P2 V2. The relationship between these two things is as the pressure goes up, the volume goes down, and vice versa. As the volume goes down, the pressure goes down, the volume goes up. So in this situation, if you're dealing with any type of gases, if you increase the pressure, that means that the volume will decrease. So essentially what happens is we kind of lower the volume in this case. So all of our gas molecules are quite near each other, and that's what's causing really the increase in collisions, because they don't have very far to go to collide with the container or anything else. So that's going to cause the pressure to go up. So in this case, what we kind of want to do is, because the change that occurs here is the pressure will go up, we kind of want to bring the pressure back down. And the way that we could bring the pressure back down in this smaller sort of volume is we would actually need less gas molecules. So in this case, if you do either of those things in a gas situation, you increase the pressure or lower the volume, it will shift to the side with the less gas molecules, or at least, I guess, now that I rewrote that, least gas molecules present. That obviously is dependent on the equation you're looking at as to which side has more or less gas molecules. You shouldn't overcomplicate the decision on that. It is just everything with a G next to it, and basically add up the coefficients for anything with a G, and it'll give you how many gas molecules. Opposite is true if we kind of lower the pressure, but increase the volume. So now what we have is a situation where our gas molecules basically have a lot more room to fly around in. And what that's going to do is basically decrease the number of collisions that's going to occur. And that's why we see the pressure start to come down in this particular case. So what we want to do actually in this case is we kind of want to bring the pressure back up because it's starting to drop. The only way to do that with a larger volume is in that larger volume, you pretty much need more gas molecules in there. So in this case, it will shift to the side with the most gas molecules. Questions on that there? So let's just say we had this. And what we want to know is, will it shift to the left, to the right, or no change? If I do the following, let's say I add some C, I remove B, I increase the pressure, I increase the volume. So take a moment for each of those situations. So C is on the product side here. So when we add, it shifts away. So we would actually expect it to head away from the product side to the reactant side. And again, the reason for this is you've now supplied a lot more products and reactants, and that's going to cause the reverse reaction in this case basically to occur because they're not going to have any trouble finding each other to basically start reacting. If we remove B, B's over here on our reactant side. That essentially like puts a hole over here on the reactant side, so it does need to shift towards that hole, and it will shift to the left in this particular case. The real reason it's actually doing this is when you remove your reactants, you once again will have more products, and more products will actually cause the reverse reaction basically to occur in this particular case. If we increase the pressure, basically that relates to a smaller volume. I personally think about it a lot of times in terms of volume. Small volume means we need less gas molecules in it. And in this case, if we add up, that's 2 gas molecules there, and one more here is 3 gas molecules on the left-hand side. On the right-hand side, that's a gas molecule, and there's 5 of them, so there's 5 gas molecules. So in this case, it will also shift to the left, as that's the side with the least number of gas molecules. Here, we're going to increase the volume. And again, in that bigger volume, the way you can remember it is you need to fill it up. So you got to need a lot more gas molecules in there to fill it up. And in this case, it would actually go to the right. Questions on any of those there? Okay. All right, the next sort of relationship we're going to talk about is temperature. And temperature works the same as concentration. So when you add temperature or increase, it will shift away. And when you kind of remove or decrease temperature, it will shift towards it. So how do we know basically which way that is? It has to do with the equation and reaction, and it has to do with what type of reaction you're dealing with. And what we're talking about is in terms of energy. So for example, if I have a reaction here, that gives off heat or energy as a product, That is what is referred to basically as an exothermic reaction. So an exothermic reaction is one that gives off heat and energy, as we talked about. And the way that's represented oftentimes in reactions is thought of as being basically a product, the temperature or heat or energy. I would say most of the time, though, the way sort of that is expressed to you as it being an exothermic or even an endothermic reaction is they will actually use that value that we saw when we talked about energy, which is the change in enthalpy, delta H, and it will be a negative value. So very commonly, they'll just give you like the delta H for that reaction. It'll be a number. And really the important part of that number is not really the number part, it's actually the sign. So if you see it's negative, that tells you it's exothermic type reaction. The other type of reaction we have is one where we kind of consider heat or energy as a reactant, like it is being absorbed, and that is an endothermic process or reaction. And in an endothermic reaction, as I mentioned, heat and energy is basically considered a reactant in all intents and purposes. And just like exothermic, probably most of the time in chemistry, this is how that is represented to you in an equation. They give you the delta H value, and it's actually going to be a positive value in this particular case. So I would say that is probably the main way that you will see it sort of represented to you. You'll have the equation. They probably won't write the heat or energy value in the equation, but they'll give you the delta H of the reaction as either being positive or negative. So what that means is if you have an exothermic reaction, and you increase the temperature, it will shift away from it. So it'll go towards the reactant side. If you have an exothermic reaction, you lower the temperature, put everybody on ice, it will be like removing that heat on the product side and it will come towards it. So again, it works the same basically as concentration. The thing you have to determine really in terms of temperature is what type of reaction you're dealing with, exothermic or endothermic. Any questions on that there? Now, a catalyst is another thing that you could do. Again, a catalyst is not a reactant. It's not a product, and it does not get used up in the reaction. Is there typically just to speed up the reaction? And again, catalysts are basically found a lot of times up on top of the arrow is typically where you would see that. If you add a catalyst, this is one of the ways that you could get kind of a no change. It'll get to equilibrium quicker, but there really will be kind of no change that's going to occur. Other ways that you could kind of get a no change is, for example, if you add something like a noble gas. Typically speaking, that will give you a no change because they're chemically inert. The other way that you could actually get to a no change situation is the number of gas molecules we were doing in the previous page. If you add up the gas molecules on the left-hand side and the right-hand side, and they're the same number of gas molecules, there is no side that's more or less. In that case, it's like a push, and it would be a no change in that case. So that's kind of three ways that you could kind of get a no change to occur. Any questions on that there? All right, then let's say we have this guy here. For the sake of argument, we'll just say that delta H is, I don't know, we'll go negative 125 kilojoules. That's clearly not right for sure. But for this, we'll do it. All right, so we want to know in each of these cases, are we shifting to the left, to the right, or no change? All right, in this case, we're going to add some N2. We're going to decrease the temperature. We're going to remove NH3. We're going to increase the, actually, we'll decrease the volume. We will increase the pressure. We will increase the temperature. We will add some H2 and we will add a catalyst. Okay, so let's take a look. So here we're going to add some N2. So N2 is a reactant. So when we add, it goes away from the side we added to. So since the N2 is on the left there, it's going to shift to the right. Again, it's going to cause really the forward reaction to occur since there's a lot of reactants. We're going to decrease the temperature here. So we want to determine what type of reaction this is, and really the number doesn't matter, but we do see the sign here, and that's negative, which means this is an exothermic reaction. And that means we can consider heat and energy as a product. And in this case, if we're going to decrease it, that would be like removing our heat and energy on our product side and creating a hole over there on the product side. And that's going to cause the equilibrium actually to shift that way in that particular case. Here we're going to remove NH3. So when we remove it, goes towards the side we removed it at. So NH3 is on our product side. So again, it kind of creates like a hole over there that you need to fill. So it will cause it to shift to the right here. We're going to decrease the volume. So once again, in that small volume, the way you can remember that is small means less. So we actually need less gas molecules in this case. If we figure out how many gas molecules we got going on, we got 1 there for this guy, we got 3 there from that guy, just adding the coefficients, that's 4 gas molecules. Over here, we really only have 2 gas molecules. And in this case, we're going to go to the least number of gas molecules, so that is going to cause it to shift to the right. Any question on those there? On the other side, we're increasing the pressure, so pressure and volume are related to each other. So really, that is the same thing in this case. It's actually going to cause the volume to go down, and it will cause a smaller volume, and it will shift the same way. So again, those two guys are sort of related to each other. If we increase the temperature, once again, since this is exothermic, if we increase it, it would be like adding more products. And by adding more products, it should go away from the product side, and it will actually shift to the left in this case. If we add some H2, H2 is a reactant, so we're going to go away from the side we added it to, so it will go to the right. And in this case, if we add a catalyst, we will get no change. Any questions on any of those there? So again, as I talked about, really what you want to think about is whatever you're doing, will it basically kick off the forward reaction or the reverse reaction to occur? And remember that one way you could do that is the availability of either reactants or products. So if you have more reactants, the forward reaction is going to occur. If you have more products, the reverse reaction is going to occur. So those are good ways to sort of think about it. Questions on that there? All right, so here's just some of the stuff we talked about. Again, when a reactant or product is added, it goes away, and when it's removed, it goes towards it. And obviously our volume change here related really to pressure. So again, it will always sort of shift that way. Again, looking at the volume, like I talked about, is a good way to do that. Large volume, more gas molecules, smaller, less gas molecules. And our temperature based on exothermic or endothermic, that's really the first thing that you want to determine. Again, delta H will be negative if it's exothermic and positive if it's endothermic. And you could think of heat or energy as either a reactant or a product in that particular case. Remember that temperature is also really the only thing that changes the value of the equilibrium constant as well. All right, so how many of the following changes would lead to a shift in equilibrium towards the reactant? So let's run through these and see what's going to happen in this case. If we remove CO, that's a product, we would expect the equilibrium to shift to the right, which means it's not going to obviously go to the reactant side. If we add O2, O2 is over here on our product side. If we add it, we'll have more products than reactants. that will cause it to shift away, so that will do one of them. If we remove CO2, that is removing a reactant, creating like a hole over here, and it will shift towards that hole to fill it, so that will also do it. And if we increase the pressure in this container, that means, again, we will have a smaller volume. So gas molecules on the left here are 2, and gas molecules on the right are 2 plus 1 is 3. And that would cause this guy to shift to the left. So it is really 2, 3, and 4 here that's going to cause it to shift to the left-hand side or the reactant side. Any questions on that one there? So one method production is described in this endothermic. How many of these would decrease the amount of hydrogen gas? So first off, it tells us it's endothermic. So this means that our delta H is going to be positive. That also means that we could think of heat as a reactant in this case. So why don't we run through this and see what happens if H2O is added? That is a reactant, so it'll go away from it, so it would shift to the right. If the volume of the container is doubled, so our volume gets larger, which means we need more gas molecules in this case to fill it. Left-hand side, there are 2 gas molecules. Right-hand side, there's actually 4. 1 plus 3 is 4. So in this case, we actually will need more gas molecules, so that will shift to the right. And CH4 is removed, so CH4 is a reactant, which means it creates a hole on the reactant side, so it will shift to the left to fill that hole. And the temperatures increase, so this is an endothermic reaction. If we increase the temperature, it'll be like adding more reactants, and that will cause the forward direction to occur and will cause it to go to the right. So in this particular question, I wanted to know what will decrease the amount of H2. So obviously this guy will increase the amount of H2 as it's going to the right where H2 is. This guy will also increase it as it's going to the right in the products. This guy will increase it. It is only this change right here, which is the one it's talking about, which is the one that will shift to the left. And when it shifts to the left, that means we're making more reactants, and that means we're using products to do that, and that will cause the H2 to come down in this case. So it will be that guy right there. Any questions on that? Now, as we talked about a little bit before, when we talk about K, which is just a number in the equilibrium expression, which again is the concentration of our products divided by the concentration of our reactants. And again, we only include things that are aqueous, are a gas. No solid or liquid is included in this expression. Now, that number, as I mentioned before, does give you an idea that when you reach equilibrium, what you'll mainly have. And if you have a large value of K, that means when you reach equilibrium, you will mainly have products. Just mathematically speaking, again, to get a large number, you'll need a large number on top divided by a small number, so you'll have more products than reactants. And if you have a small value of K, that means that you would actually have more reactants when it reaches equilibrium. And again, mathematically, to get a small value, you would need a larger value on the bottom here when you're dividing to get a small value in that case. A value of 1 is considered large, so anything above 1 is large. Anything less than 1 is considered a small value for K. Now, the value of K can be calculated if you know the equilibrium concentrations. So if you do have the equilibrium concentrations, you could put it in there. Like we talked about, you do need to take into account the coefficients when you do that calculation. So K would equal the concentration of C to the C, D to the D, A to the A, and B to the B. And they do have to be equilibrium concentrations to basically go in there as well. So the equilibrium lies to the right. The value of K would be large in this case. Again, that's going to tell us we have more products than reactants. And it would be small if it went to the left. Again, that would be really small. So there is, as I mentioned, I think the other day, sort of extremes to that. There are really, really large values of K, like times 10 to the 34 or something like that. And there's really, really small values of K, like times 10 to the minus 56. So super small values, super large values, and really values all the way in between as well. So you can have really any type of value for K. All right. So for example, here, if we wanted to calculate uh, the equilibrium concentrations in this reaction, we can, from the initial concentrations, we have to do a different type of calculation. And in this particular case here, we have the equilibrium concentrations of two of them, but not one. So we can use our expression here and write our equilibrium expression, which is our products, which would be HI squared divided by the concentration of our reactants, which is H2 and I2, and this would equal 50. In this particular case, they gave us the equilibrium concentration of HI and I2, so we could actually put that in there. That would give us 5 times 10 to the minus 1. We do need to square it, divided by the concentration of H2 that we're looking for, and our I2, which is 1.5 times 10 to the minus 2. That would equal 50. We want to multiply the H2 to both sides. They will cancel. And we also then want to divide the 50 back to the other side after we do that. And if you do that, you'll get pretty much the setup on the bottom there. You'll get the 5 times 10 to the minus 1 squared divided by 50 as it comes to the other side. And 1.5 times 10 to the minus 2 will equal our H2 concentration. And I'm assuming this box there, so that hopefully should be the right answer, but let's double check. You never know, I suppose. Squared divided by 50 and divided by 1.5 to the minus 2. It's going to give us 3.3 times 10 to the minus 1. So in this case, if you do know the other equilibrium concentrations, you can figure out a missing equilibrium concentration at this point. Any questions on that calculation there? All right, so we're going to talk about a special type of equilibrium, which is known as KSP. And KSP is the solubility product equilibrium. And it really is the equilibrium for things that are insoluble. So this is kind of the equilibrium for insoluble things. Like in our solubility rules, when it says something is insoluble, it will still have some degree of solubility. So even things that are technically insoluble, for example, like silver chloride, based on solubility rules, that is insoluble. But in solution, a little bit of it will break apart into silver ions and chloride ions, and will set up an equilibrium. And you could write an equilibrium for this, which is our products over our reactants. But in this particular case, and in most KSPs, there are only solid on the reactant side, and that's not included in the expression. So when you write the equilibrium expression for a KSP, typically it's just the products because the reactants are always solid, so they're just left out of this equilibrium. So here's another example of that. Again, we have our solid going into our aqueous ions. We could write our expression again, our products, which is BI. We do need to square it because of the coefficient, times S2 minus, and we do need a cubit because of the coefficient. And again, here we would not include our reactants because it's a solid in this particular equilibrium. These KSP are solubility because they are really for things that are insoluble and typically will be a solid. They typically are very small values. So these are very small values. And the reason for that is how these reactions are written is pretty much what you see there. Typically on the left-hand side, you have your solid, and on the right-hand side, you have your aqueous ions. And because this equilibrium is typically really small, that means most of the time it is hanging out over here on the reactant side. You mainly have reactants. When I talk about small here, I'm talking like times 10 to like the minus 34, super small number. Yeah, so really, really small. And that only way you could really get something that small is you need to have a lot of reactants versus products. So it's mainly going to be staying together and going to make that precipitate, which is why we consider these things to be insoluble, and they will make a solid because pretty much, although a little bit of it will break apart, it's pretty much just going to kind of hang together and stay together. Questions on that there? So if we want to determine the value of, say, the KSP, and we know the concentration here of our lead 2 chloride, we could kind of do a calculation, and we'll just talk about this calculation actually first. I'll do it here. So when we do equilibrium, we do a calculation that you will never see until you get back into 1B, but this is what is referred to as an ICE table. And an ICE table stands for initial, change, and equilibrium. And we use these when we don't know the equilibrium concentrations, but we only know the initial concentrations. So for example, we take that one we just looked at, H2, and it was I2, I think, and it went to 2HI, and it had a K value of 50, for example. Now let's say in this case we had an initial concentration of H2. Initially, we'll go with 2 molar. And we had an initial concentration of I2 that was also 2 molar. And we want to know what is everybody's equilibrium concentrations. So the way that we do this is we would initially here in our ICE table just put our initial concentration. So that's 2 molar, that's 2 molar. And typically speaking, if you are not given anything about the products, you could just put 0 initially. You don't have anything. Now, the change part's actually really the important part here. And in this particular case, the change is going to be as this reaction takes place, because we have no products, we could safely assume that this reaction should head to the right-hand side. And what that means is the reactants that we have should actually be decreasing with time because the forward reaction is happening. And the product should actually be increasing with time because it's making them. The way we represent that in this ICE table in the change part is with minuses and pluses. And whatever's decreasing is represented as minuses, and whatever's increasing is represented as pluses. And the change is typically represented with an X. So we typically use X as our kind of unknown. So this would be minus X because it's decreasing. And when you do this part of the calculation, you do need to take into account the coefficient. And in this particular case, the coefficient is 1. So it's basically like 1x, so you don't have to put the 1 there. This would be minus x. This coefficient is also 1x, so you don't have to worry about it. Now on the product side, it should be increasing, so this would be plus The coefficient here is actually a 2, so you need to do 2x. Those coefficients take care of the mole-to-mole relationship. It does the stoichiometry for you, all wrapped up together. And if you don't have those coefficients there, you're going to have really the wrong relationship. So you want to do that. Now, when we get to equilibrium here, we will have 2 minus x, basically, 2 minus x, and 2x. First off, any questions on sort of this table? What do we do with this table? Well, we take our equilibrium expression, which is hi squared divided by h2 and I2, and that equals 50. And what we do actually is take everybody here in the equilibrium line and put it into this equation. So that would give us up on top 2x, and that's going to be squared, divided by 2 minus x times 2 minus x equals 50. The goal here is to actually solve for x and figure out what x is. In this case, if you can't see it, this is actually a perfect square on both sides. So if you can perfect big old square root on each side, that will give you 2x on top, 2 minus x on the bottom. And the thing I typically forget to do is actually square root the 50. So we do want to square root the 50 there. And that is going to get us 7.0711. We now want to solve for x, so we're going to multiply this to the other side. That will give us 2x is equal to 14.142 minus 7.0711x. I need to then add this back to the other side to combine my x's together. And if I do that, that will give me 9.0711x equals 14.142. Lastly, to solve for x, I'm going to divide this to the other side, and that will get me an x value here of 1.56. First off, any questions on that there? Now, what that allows us to do in this case is figure out now the equilibrium concentrations as we have now figured what x is. That x value is every x you see in this table. So that is basically all those values there. So what we could do now basically is go back into this table on the equilibrium line. I'm just going to erase this so I got somewhere to write. And what we can do is figure out the equilibrium concentrations. So if I now want to know what the equilibrium concentrations of H2 is at equilibrium, I can see from the table it is 2 minus x, which in my case would be 2 minus 1.56 molar. That will give me a concentration for this guy at equilibrium of 0.44 molar. I could do the same thing for my I2 at equilibrium. It will be equal to 2 minus x, will give me the same number in this case, 0.44 molar. I could do that for my HI. From the equilibrium line, it equals 2x. So I'm going to go 2 times 1.56 molar, and that will get me 3.12 molar. This would be the equilibrium concentrations of all these guys at equilibrium. We see what we expect. We started with 2 molar of H2 and I2. At the end of the reaction, it decreased, right? So it went down for sure. This is reactions heading to the right, and we ended up with only 0.44 left over. We also started with none of our products, right? But we actually made a lot of products, right? So we ended up with 3.12. First off, any questions on that calculation there? You can check this because it is a math problem, basically. Now that you have the equilibrium concentrations, if you put those numbers back in, to here, you will basically get 50. You'll get a little bit more than 50. It won't be exactly 50 with rounding, but you should get in the ballpark there of 50. And that's a good way you could kind of check yourself. Any questions on this calculation here? Okay. All right. So let's see how we could use that in this situation. If we have this problem here, this KSP problem, we can look at the equation, and basically this is what's going to happen. We will have our lead and our chloride breaking apart. If we write our KSP expression for this, again, it's our products, which would be our lead 2, and our chloride, which we do need to square because of the coefficient. Now, in this case, it's prepared by dissolving some salt in water, and the lead concentration is determined to be 1.6 times 10 to the minus 2. So you could do one of two things. You could actually use like an ice table in this case and get sort of your answer. So for example, if you did your ice table here, we would actually start with zeros here. And on our reactant side, we wouldn't worry about it because it's a solid. It's not going to go into our expression, so you don't have to put any number there. We could do our change. This is going to be plus x and plus x, basically. And not just x, but that last guy is going to be plus 2x, right, because of the coefficient. So you got to make sure of that. That means at equilibrium, you have x and 2x. If you go into your KSP expression, that basically is x times 2x squared. Now, one of the things that it told us in this problem is at equilibrium, the concentration of lead is equal to this number. And if we go to our table, that is exactly what x equals, right? We can see that is lead ions. At equilibrium, it equals x, and they told us what it is. That means that all we have to do at this point then is put it into here, and 2 times that, and we still need to square it as well. So if we do all that, we will get probably what it says there, I would hope. And we're going to square it times 1.6, make sure we use our exponent buttons, and we will get that 1.6 times 10 to the minus 5 there would be our value. Again, this is an equilibrium expression, constant, so we don't need any units associated with it. It's just the number in this case. So you could definitely use the ice table to do that. You could also use what we talked about in class when we did concentrations. It is a 1-to-1 relationship between these guys and a 1-to-2 relationship, or a 1-to-2 relationship, so you can figure out the concentration and just go into the expression. Any questions on that there? And lastly here, we'll take a look at one last one here to wrap it up. So we want to calculate the solubility of silver chloride in water. This case, they only gave us the KSP. So in this case, you do have to do an ice table. And we would take our silver chloride, and again, we will break it up into its ions, which is a silver ion and a chloride ion. We could write our KSP expression for this, which would be our products over our reactants. And again, we're not going to have any reactants in this case because it is a solid. This equals 1.6 times 10 to the minus 10. So that is the K value basically here. So if we do our ice table like we just saw, we could go 0 and 0. Change would be plus x plus x. That means at equilibrium, x and x. Once again, we're going to ignore this side because it's solid, so it doesn't get involved really any here. If it wasn't a solid, you wouldn't ignore it, obviously, like in the first example I did. But here, because it's a solid, you could ignore it. Now, in this case, we're going to put this into our equilibrium expression, and that will basically give us x times x is equal to 1.6 times 10 to the minus 10. That basically gives us x squared equals 1.6 times 10 to the minus 10. A little square root action on both sides. That gives us an x at this point of, go with 0.000013. I guess that is 1.3 times 10 to the minus 5. So what is the solubility of this silver chloride? This is molarity in this case. So what we just calculated here is molarity. That is the concentration of silver, and the concentration of chloride would both be 1.3 times 10 to the minus 5. Because it is a 1-to-1 relationship going backwards, that is also the concentration of silver chloride. So typically when you solve for X in this type of equilibrium, this KSP, whatever X is the molarity of your solid. It is also what is referred to as the molar solubility of it. This is really the molar solubility, which is our moles per liter. If I want to know how many grams per liter, you would use the molar mass. So that also is sometimes used in these type of problems with KSP. You want to know what is the solubility, how many grams per liter you could get to dissolve. You can multiply the molar solubility or molarity by the molar mass of the compound, and it'll tell you basically how many grams you could do that. So, whatever, silver is in this case, you would find out that, you could dissolve, for example, something like 0.002 grams of silver chloride in like 1,000 milliliters of water. And that's a very, very small amount, which is why we think of silver chloride as being insoluble. Question on equilibrium. All right, that wraps up this class, I think, in terms of the lecture material. Any questions on anything? All right, a couple things. We're obviously going to